you very much. And thank you, Valeria, for letting me come here for these 2 days and for asking me to give a talk, which I am very happy to do, although it was a little bit short notice. I was wondering whether I had anything of interest to tell you. And of course, I also saw the list of talks, so I saw that the really broad programs, and then that got me a little bit less worried. But so I simply going to talk about my latest work, some joint work with Anton Zetzel, with the title that we already heard. So maybe just to put it in some context, I have been in Gothenburg since the early 80s, even since before there were any proof assistants at all, and only a few years after the Gothenburg group started working on Martin-Löf type theory. The way it started was that Martin-Löf contacted the most senior computer scientist at that time, who was about like 28 or something. He had written this paper, Constructive Mathematics and Computer Programming, where he really suggests that his intuitionistic type theory can be used as a programming language. And the idea of this group, which was then formed, was to somehow put Martin-Löf's ideas in practice. And I would say that this is what has happened during more than 40 years now. And although, of course, the work has expanded and renewed, I would still say very much that it is very much in the spirit of what Martin-Löf was laying out. Of course, homotopy type theory has been a great new development, but it's nevertheless, in my view, very much a continuation of earlier ideas. So, I understand that this program, it's formal mathematics in very many different systems and very many different aspects, and a lot of emphasis on informalization as well. In Gothenburg, we have almost exclusively, in our group, I should not forget that there is another group on formal methods. Moa Johansson from that group was here. So we have another group which does not work with Martin-Löf type theory with our system, but the type theory group has almost exclusively worked with constructive type theory, intuitionistic type theory. Of course, the notion of logical framework has been important, but we have not really exploited the possibility of using a logical framework for doing classical mathematics. And what was very important in the early days in particular was, we were under the spell of Martin-Löf, and all the discussions about foundational reasoning were very lively at the time. So notions such as predicativity, was very often some kind of topic of lunch discussion, so as to speak. Predicativity and constructivity come together in Martin-Löf's system. He uses the word, he claims his system is both predicative and constructive. So I just drew this little square, that in the world of systems, there are constructive ones and there are classical ones, and there are predicative ones and there are impredicative ones. And all the different combinations are of interest in the history of suggestions for formal systems for mathematics. Of course, in the early days there was a lot of discussion of the sort of Martin-Löf predicative type theory versus the calculus of construction, the impredicative type theory, where calculus of inductive constructions is kind of hybrid between Martin-Lövian ideas, but also including the original calculus of construction. These discussions have kind of died down a bit, so today is an opportunity to wake them up a bit again. So, the other word in the title was Mahlo universe. So in order to just give an introduction to the Mahlo universe, it's just simply to display the definition of the original notion of Mahlo. Mahlo was someone who worked very early on in set theory. Already in, I think it's 1911, he wrote some papers introducing the notion of Mahlo cardinal. And in order to explain this, we have to start with what does it mean to be an inaccessible cardinal, a cardinal that kind of goes beyond the ordinary ZFC set theory. So what it says in the first display here is that, so-called strongly inaccessible cardinal is something which is transfinite, it's bigger than atom 0. It's closed under 2 to the alpha function, and so this is also called a strong limit cardinal, and it's also regular in the sense that it's closed under indexed least upper bound. And what is interesting about this is that if you have a strongly inaccessible cardinal, I, then, and let me again pull this up a bit. If we have a strongly inaccessible cardinal, if we draw this picture of the cumulative hierarchy, and we have a strongly inaccessible cardinal, here is the ordinals, and then you take the cumulative hierarchy up to I, the VI, then this is, well, it's a Grothendieck universal set theory, but for our purposes it's more important that it's a kind of universe which is closed under all the standard type formers, pi, sigma, 0, 1, 2, natural numbers, W types, and identity types. So this talk is actually going to be technically about the set theoretic model for type theory with the so-called Mahlo universe. But philosophically, it's going to say that this is just to support some much more basic reasoning of why this is kind of constructively and predicatively valid. Okay, so a Mahlo cardinal has a further closure property. It says that, there is something called a normal function in set theory, which means that it's strictly monotone and continuous. And if that is a function from an inaccessible cardinal M to M, then M is Mahlo, provided it has an inaccessible fixed point which is smaller than M. And if it has that, then the restriction to this fixed point is a function from this fixed point to itself. So I'm somehow showing you this in order to explain what the notion of Mahlo universe comes from. I will explain then how this appears naturally in type theory by kind of elementary reasoning in some sense. But it really comes from modeling this situation in a type theoretic setting. So the analog will be that this will be a Mahlo universe, and what is typical for a Mahlo universe is that for any kind of function, so as to speak, on this Mahlo universe, or then there are sub-universes which are enclosed under this function. I will come to exactly what this means. So just a little bit of a history of the notion of predicativity. It started with Russell and Poincaré trying to kind of have this idea of how to build up mathematics safely. And one of the big contributors, the mathematician Weil, who was very interested in foundations. And so he introduced the notion of predicativity given the natural numbers. The natural numbers was something that we had to take for granted. He worked in a classical setting. So there, if you're interested in the history of predicativity, there is a very nice paper by Pfefferman, where, for example, it is explained why the ordinal gamma 0 is considered to be the limit of predicativity in a certain sense, and this has taken root in proof theory, so that often this is what's the way that the term predicativity is used in proof theory. And as it happens, the original version of Martin Löw type theory with a whole sequence, an infinite sequence of universe, has the strength gamma zero. So it's some kind of support for the fact that gamma zero is predicative also in Martin Löw's sense. But people have gone on and continued building bigger universe, like a super universe. I will explain what that means also in a moment. And then you get something which is kind of similar to the original notion of predicativity, but it's not called but it's got a bigger proof theoretic order, and so the term here is meta-predicative. But something which was definitely not considered predicative are the W types. On the other hand, Martin Löw, he still calls his type theory predicative, although he introduced W types at some point. And so this talk is about the notion of extended predicativity, and by that we mean predicativity as Martin Löw understands it. So one could kind of hypothesize that it means to be generalized, inductive, or inductive recursively defined. I will explain in a moment what the inductive recursive definition is, and that this is constructed in the sense of Martin Löw. But it's not obvious, and I shall explain why it's not obvious. So the third word in the title was inductive definition, and this is a quote from Martin Löw's first unpublished paper on type theory, where he explains the relationship between inductive definition and type theory. So he says, the type N is just a prime example of a type introduced by an ordinary inductive definition. However, it seems preferable to treat this special case rather than to give the necessarily much more complicated general formulation, which would include sigma plus finite types and n as special cases. And then he refers to his paper from 1971, where he has a schematic presentation of inductive definitions in first-order predicate logic. So here he doesn't actually anticipate W types or higher universes, but nevertheless it's a clear sign that type theory should be understood as a theory based on inductive definition. Another piece of evidence for this view is Peter Axel's article in the Handbook of Mathematical Logic, written in 1976. Then Peter Axel had already worked on type theory for a few years. So he said something like, it would be interesting to have a framework that makes induction the principal notion. He doesn't say that it is Martin Löw type theory, but I think it's clearly influenced by that. Okay, so let's look at the W type. So the W type, what they are is a type of well-founded trees with arbitrary varying branches. So you have a set, so I should also introduce the notion of, Martin Löw was a bit somehow ambivalent about what to call the basic notion set or type. And in the version of type theory that we are using in this talk, we have both notion of set and type. So set is kind of small type, but it is actually a type, and therefore we can write A colon set. A is some kind of index set, where you index the branching factors. So B takes an index and gives you a set or the sets that you branch over. So here, right, is that if you have an index and then you have this big B here, if you apply big B to A, you will get some type here, and you can now index over that type or set. And then you can build a bigger tree which has those little b's as subtrees. And because A can vary, it's varying, and because B of A can be anything, even when we introduce universes, you can even have the universe as a branching factor. So it's a very powerful notion. And there are some results that say that this is somehow canonical for generalized inductive definitions in type theory. This capture all the strength. You can actually encode all the inductive types which are natural to have in type theory. So there is a general schema for inductive types, which is just a mild generalization of W types. So first of all, you have several constructors rather than one that you had in the W type. And then you have several index types. And then you have several ways of having subtrees with different branchings. But as you see, the pattern is very similar. It's just that you take one constructor, and these are called side conditions. The little a in big A, little a, m in big A, m. While these I call inductive premises, and since they are function types here, they are generalized. You have a generalized inductive definition. They can be infinite and arbitrary branching. And such a definition can depend on parameters such as the big A and big B in WAB. So the question then, when you have you try to understand the general pattern behind multi-level type theory, is where should we place universes? And what really makes this theory take off is that we pass from the so-called notion of universe a la Russell, where a universe is a type of types, to a universe which contains codes for types. So you have to distinguish between the big U here, which is the universe, and you have a function which takes an element in the universe and decodes it to a so-called set. I will come back to this as well, why we have this distinction. And then we have two ways. For example, we say that the universe is closed under W types. We have W hat, which builds codes for W types, and id hat, which builds codes for identity types. And then we have decoding function. I mean, this T here, it computes. So T of W hat returns a W, and T of id hat returns an id. And if we look at this and compare it to the structure that we had on the previous page for inductive definitions, we see that there are lots of similarities, but now, so this fits the general schema for inductive types, except that both non-recursive and recursive premises can depend on earlier premises via the T function. So you see here that the introduction rule for W hat, it has a T of A here. It's very similar to the introduction rule for the W type, but the difference is that the T is defined simultaneously and that it computes. And here is another interesting phenomenon is for the code for the identity type, where you see that the side conditions, they depend, they are elements of T of A, so they depend on a recursive set. So this is the step when you realize that you can generalize your schema by doing this kind of simultaneous inductive recursive definition. Then you somehow, almost by magic, get something very strong, which can have many special cases. So in particular, me and Anton, we defined a finite axiomatization called IR in a joint paper in 1999. And you can see that there are lots of special cases, all the, the Tower of Universes Alatasky, Erik Palmgren's internalization and the super universe, and also the Mahlo universe that Anton had defined a few years earlier, sort of independently of when I had kind of started thinking about inductive recursive definitions. So by some kind of coincidence, this was subsumed in the sense that the so-called sub-universes of this Mahlo universe would be an instance of an inductive recursive definition. But it also has limits, because if you try to make the Mahlo universe internal, by not saying that it's not set itself, but it's something inside set, then it goes beyond this schema. And then Anton has continued investigating even bigger things. So, as we suggested, there was a strong correspondence between W types and generalized inductive definitions, if this is the theory of that. There also seems to be a strong relationship between Mahlo and these inductive recursive definitions. Okay, so the setting here is Martin-Löw type theory as he defined it in 1986. Martin-Löw was very influenced by the work on the calculus of constructions. So he particularly liked what he said called the high level notations that you could have in the original calculus of constructions. So he came back at the workshop in 1986 and he said, you know, I have introduced the same high-level notations, but I have disentangled it from impredicativity. So what he did then was that he formulates type theory in two levels. There is the theory of types, also called a logical framework, which contains very little. There is the type set, which we introduced before, and there are dependent function types. And that's all you have on that level. Sometimes you can introduce, you know, dependent pair types as well. But with this kind of basis, then you can formalize the whole theory, all the standard set formers and a lot more, just by adding constants. So this theory so this is what Per Martin-Löw considers to be the standard version of type theory nowadays. And these theories that Anton and I worked on, they are based on this formulation of type theory. And in this talk, we consider type theory with a Mahlo universe, and it's also based on that. So Agda is loosely based on the logical framework, but it differs in some respects. And the reason is that Thierry is not Per Martin-Löw. And when Thierry decides on having a theory, he doesn't ring to Barnhetsgatan 4 in Stockholm, but he has kind of deviated a little bit, right? And that's why you have an infinite hierarchy of universes. While Per insists that there should only be one, this special universe of sets. So of course, set here has nothing to do with with H set in the sense of homotopy type theory. It's just rather to think about as small type, or as kind of even sort of some way of internalizing what was type in the early type theory. And then, so the point is now that, you know, we can now define various constructs in the theory just by adding constants with their types. U is in set, T is a function from U to Z. These are the types of W hat and id, and well, the equations look the same. Right, okay, so let's see how you go further. So the first step of taking type theory into the sort of higher infinite was taken by Erik Palmgren in 1991, who internalized the external universe hierarchy at Tarski. So he introduced an operation, you know, plus, that takes a family of sets, you know, a universe Alatarski is a family of sets, T naught is indexed over the index set U naught, and returns the next. So if you take the ith universe, and with UITI, and you apply the plus operation, then you get the next UI plus 1, TI plus 1 in that sequence. And then you can say, well, now we can have a more powerful universe called the super universe, which is a universe, it's closed under all the standard set formers, and it's also closed under this plus operation. But there is no reason to stop. You can have the next super universe operation, and you can close up under the next super universe operation and get super universe. So what we call the external Mahlo universe takes one further step of generalization. He says that not only next universe, next super universe, next super universe, we can close up under those, but we can close up under an arbitrary operation which takes a family of set into a family of set. Of course, this starts feeling a bit dangerous because we sort of build sets by kind of quantifying over, functions between families of sets and families of sets, and this is suspiciously negative, and, will this really work? And this is what makes this interesting. So we call it an external Mahlo universe because it's set which corresponds to this. I didn't write it there, but this Mahlo universe or Mahlo cardinal, and the universe which you get by closing up under this is F0, F1 maps. Those correspond to the sub-universes. Okay, so just a little bit how this is formalized in type theory. We have written this in IDA. So it just says that U is now something which takes a family operator, F, split up into two arguments. One that takes a family and returns the index set, and one that takes a family and returns the family, so as to speak. And there is both the U and the T part. The T decodes the elements in U, F0, F1. And then, you have to close, in order to close U, F0, F1 up, they should be closed under F0, F1 in the Tarski style. We have to introduce constructors C0 and C1 that takes kind of small such families and returns small such families. And when we decode them, we should, so C0, X0, X1 will be a small family. And now we apply F0 to the decoding of X0 and X1. And then the other component is obtained by taking F1. And then it should be a universe, so we have constructors for code for all the standard set form, and we call the resulting theory TT with this Mahlo universe. Okay, so now one might think that these kind of intuitive spheres, they were vindicated because Erik Palmgren, he added a natural-looking elimination rule to the Mahlo universe, and he derived an inconsistency. But then, I was not at all worried about this, because I thought, well, this is absolutely unnatural and the wrong thing to do, because it amounts in our formulation to have an elimination rule for the type of sets, which is supposed to be open to extension. So you shouldn't eliminate over something which is kind of open to extension. On the other hand, you can have an elimination rule for the sub-universes, and this is really part of what you get from this theory of inductive recursive definitions. But then, if you now introduce an internal Mahlo universe, where you go one step further and you introduce something which is an element of the type of sets with its decoding now it has to be a la Tarski, then it would be natural to have an elimination rule and then we would get an inconsistency. So this is very puzzling, because actually the two theories are very similar, but why should it be that the one is okay and why is it not? It's with a kind of philosophical argument. It's technically, although you may be persuaded by philosophy, but technically this is a bit weird. So Per Martin Löv, he wrote his so-called meaning explanations, which, to this date, I would say, is the most convincing explanation of what constructive predicative mathematics means. But then when he introduced the logical framework with a distinction between sets and types, he had a different story. And it seemed to me at the time, as the story he had convinced me that it would be okay. But this talk is in some sense saying that I think you can do better. but this is also another sign. Maybe we have reached a natural limit for extended predicativity. And when I reread this paper, I was sort of quite shocked that we had written, oh, this is maybe the limit of extended predicativity. And then I thought, oh, it must be Anton who wrote this sentence. Yeah, anyway, so what we do now is that we do two things. One, we build a predicative model of this theory with the Mahlo universe, in classical set theory, extended with a Mahlo cardinal and an inaccessible cardinal above it. This is one thing. This is sort of, in some sense, purely technical work. And then we say that because of the way this is built, this explains why we can extend the meaning explanations, or extend Martin Löf's meaning explanations that he had for the ordinary type theory to this type theory with the Mahlo universe, and somehow convince us that this is kind of fundamentally okay, because here, you're supposed to think about what is constructively valid in a primitive sense. You're not really allowed to say that it's okay because you can formalize this or that in another theory. You have to sort of understand it in primitive terms. But this work on building a set theoretic model is useful for sharpening your intuitions about what it is like.
Yeah. A while ago, but didn't the whole thing come from the 86 version instead of the 79?
Yeah, so the 79 version is the one where he discusses these meaning explanations, the computation to canonical form. Then in 86 he added this kind of extra level, which he kind of thought about in some sense as a meta level, and where he thought he should have a different way of explaining it. And he has written a lot about this, but it tends to be of a more philosophical than technical nature. And this is in some sense the challenge. How do we, because in order to justify this, we have to kind of record, if we want to follow him closely, we have to sort of look at what he wrote. And this is in some sense saying that we should be more close to what he did in 79, also for the logical framework level. Or put it differently, we should be more Martin Löf than Martin Löf himself. So I have, so this is something actually very important for if you work in type theory. One of the most kind of simplistic models you can make of type theory is to sort of say that everything is in type theory is interpreted in set theory in the natural way. When we have these kind of large universes, we have to kind of relate them to the large universes, well, various kinds of universes in the sense of set theory. So I already said, that if we have an inaccessible cardinal here, then B of I is closed under all the standard set formers. What we want to do now is that we, so first show this picture a bit more. So actually we will have an inaccessible cardinal, but it will be above a Mahlo cardinal. And the reason is that we will kind of we will interpret the types in the logical framework up to this in the cumulative hierarchy up to this inaccessible I, and the sets. So the sets will be interpreted down here, and the types, they will be interpreted up. Yeah, some of them will be up here, and some of them will be down here as well. And then, we have the Mahlo property, which makes it possible to look also at, if we have some kind of function on families here, F, then we can, do a little bit of set theoretic fiddling, and we can see that we get a kind of cardinal here, where the sub-universes will live. So, yeah. So you can make a model where we simply interpret type as this part of the cumulative hierarchy, the sets as this whole cumulative hierarchy, and the subuniverses as this part of the cumulative hierarchy. But from the point of view of supporting the meaning explanations, we will have something a bit finer. So we will somehow inductively generate, in some sense, the definable types, the definable sets, and the definable elements of the subuniverse. So with this,
sorry, definable set is not below set? No, sorry.
So let's see.
Sorry.
So set is all this piece. Yeah, it becomes
okay.
Yes. Yeah.
Okay. Sorry.
So as you see here, right? So we start by we can inductively generate the types. They will be a subset of V of I, and then we can inductively generate the context. They will also be a subset of V of I. These are the context morphisms. They will just be ordinary set theoretic functions between the contexts, and the terms, they will be somehow in terms of type sigma in context gamma. The set of all such terms will be the pi type over, indexed by the context, and sigma depends on little gamma, right? And then we inductively generate all the good sets, and we inductively recursively generate the subuniverses, which will be Tarski style. And somehow everything here is in some sense well known, except what I call the key step here in generating the Russell style set. And we will do it in such a way that the subuniverses are closed under all the standard set forms, and the operator, the family operator F. And set should contain all the UF not F1 and closed under the standard set formers. And type should be closed under pi types, the set of sets itself, and the set should be a subset.
How many of these are defined?
Sorry?
How many of these are defined sort of mutually? Like of these six, which of them require also doing the others at the same time? Or can it be done?
So that's actually a very good question, right? And so they aren't defined mutually, and the somehow deep reason for this is that in set theory we can kind of define things without knowing that it's okay from the beginning. We can kind of do a more general definition. I will show you exactly how that happens. So in order to show this, we shall show the inductive definitions using a nice formalism which is in Peter Axel's handbook article. Often inductive definitions in set theory are defined by fixed point or monotone operators, but he introduces a formalism where a rule UV, you have to start with a base set big U. It's a pair of a subset of big U, set of premises, and V, a conclusion. And then you can define what it means for a set W to be closed under a set of such rules. And it's the obvious definition that if U, the pair UV, is in that set of rules, and U is a subset of W, then V should be in W. And then you can, by set theoretic means, show that there is at least such phi closed sets. And of course, the irony here is that this is a typical impredicative definition, right? So first step here is, how do we define the Tarski style subuniverses? And this is somehow known since the 1980s from Stuart Allen, New Pearl, member of the New Pearl team. You can get set theoretic semantics for universe a la Tarski by defining the graph of that function. So let's just look at this rule here. So it says that the set theoretic meaning includes the pair C naught XY, F naught big X, big Y. If you remember the computation rule, it said that C naught xy was mapped into F naught over the decoding of little x, which is big X, and the decoding of little y, which is big Y. And this is what is one of the premises, is that little x decodes to big X, and the other is that little y for each z in little x decodes to big Y in little x. And then you have to do a little bit of set theoretic work in order to show that this is really a U set on in this case, the V kappa F, this kind of sub-universe that or the cumulative hierarchy up to a certain cardinal. And the other one is somehow the same idea, so I won't go through that in detail. And then the dots here is that we have to kind of have rules for all the ordinary set forwards again for the universal Tarski. And then comes the key picture here. Normally we wonder when is U F naught F1 a set. So we have rules for generating sets, which is the meaning of the type of sets. So we want to know when is U F naught F1 a set. What are the premises? And the first try would be to say that, well, it's as soon as F is a family operator, we should put UF naught F1 into set. But you can't really do this in this formalism because of the negativity. Instead, you have to do a slightly more clever step, which is originally due to Ulrich Berger. Say that it's actually enough if we know that the F maps kind of small elements of in the sub-universe, two families of sets. As soon as we know for a certain F that this is the case, then we can put UF naught F1 into set. And this definition is for completely arbitrary Fs in going, over this whole very big families over the VM up to this cumulative hierarchy. And then it's actually not difficult to prove that this yields a model of the theory. But the situation is interesting because it's not, you have done something a bit unusual. Yes, thank you. So you have done something a bit unusual because usually, in the meaning explanations, the kind of, let me say that in the next slide instead. So we now want to give a meaning explanation for this theory with Mahlo universe. So it's just sort of same as Martin Löw does in his 1979 paper, but adapted to the logical framework version. But where we also had to sort of treat set as he treats an ordinary universe in 1979. And then we have new canonical forms because, U applied to F naught F1 is a canonical form, irrespectively of what F naught F1 are. They don't need to be normalized. And also the constructors for this sub-universe are also normal, also generate normal forms. And here it's important that it's some kind of lazy evaluation, so that for arbitrary A naught and A1, C naught of A naught A1 is a canonical form. And then we have the computation rules that were already on the previous slide. And here comes in some sense the crucial slide here. So you can think of Martin Löw meaning explanation as what you do in order to justify a certain judgment in his theory. You need to have the canonical form of the term, the canonical form of the type, and then you have certain conditions relating those to each other. So if the canonical form is UF naught F1 and the canonical form of the type is set, then this judgment is valid under the condition, and this is more or less the same as was written in the set theoretic rule. Basically, you're saying that it's enough if you test F naught and F1 on small families rather than on all families, on families with small families as inputs. And this breaks the pattern because in the meaning explanations, it's always the case that the formation rule gives you a kind of a matching condition for the set former in question, and the introduction rule gives you a matching condition for the term constructor in question. But here it deviates from that pattern, and yet it's a good explanation. So something which is also important, but which is often a little bit implicit in Martin Löw's writing, is that the repeated process of lazily computing canonical forms and checking matching conditions must be well-founded. Something is a natural number is only the case if the process of computing successive canonical forms, finitely many successors with a final matching 0. If we get an infinite sequence of successors, then the judgment is not valid. And we can have a similar discussion that, you know, in the matchings for a W type yields a kind of well-founded tree. And well-foundedness is a non-trivial issue for the Mahlo universe for a reason which is intimately connected with Almgren's paradox. If you try to have the naive matching condition, you will get a non-well-founded matching situation. So hence, that wouldn't work. That couldn't justify. So the final slide then is that Martin Löw wrote a paper about the meaning of intuitionistic predicate logic. It was called The Meaning of the Logical Constant and the Justification of the Logical Laws. And there is the split between the meaning of and the justification of. And this is really important, I think, because this is very often confused by people in the discussion of these things. There are the meaning explanations which express what the judgments of type theory mean. This is in some sense as unambiguous as you can imagine. It's like some kind of informal or formal type checking procedure. But when we justify a rule, we have to kind of predict in advance that this kind of type checking procedure will be, you know, well-founded and will be okay. So it's something kind of inevitably subjective about it. And there is this famous statement of Martin Löw at the end of his 1979 paper where he says, very appropriately, but there are also certain limits to what verbal explanations can do when it comes to justifying axioms and rules of inference. In the end, everybody must understand for himself, herself. It was the 70s.
You want to say themselves.
Themselves is the right, yes. But on the other hand, we may use any means at our disposal for reaching these kind of insights. For example, mathematical model building in set theory. And when we justify the rules of type theory with set as a Mahlo universe, it parallels the proof that a set theoretic model is a model of type theory. So this is not a proof, it's just something that suggests something. But you have to sort of realize something more, because there is the correspondence between the real process of this kind of type checking and its representation inside set theory. And it's very often that people say, Martin Löw meaning explanation, it's just realizability. But this is not right. And it's not necessarily the case that building a realizability model is actually better than building a set theoretic model of this kind, although it has certain advantages.